Welcome to Zoominario. Today we're very excited to have Ulises Rosas P. Ulises was born in Lima, Peru. He earned his bachelor's degree in biology from Universidad Nacional Mayor de San Marcos and his master's degree in biology from George Washington University. He's currently completing a PhD in ecology and evolutionary biology at the University of Oklahoma. Thank you, Ulises.
Thank you, Claudia, and thank you for you being here and organizing this wonderful event. Well, I'm going to talk a little bit of how can we obtain phylogenetic networks in more efficiently you want. But let's talk a little bit about what is a phylogenetic network, right? We can think of phylogenetic network like a, a diagram or how to model hybridization integration in this network here. And usually in this inside this phylogenetic network, we can find multiple phylogenetic trees embedded on it, right? In this case, we have two. And if you have phylogenetic network, you kind of have a bigger picture of how the species evolve over time. And so that's why it's important to obtain phylogenetic networks. The way that we typically do that is by using something called concordance factor table. And you can see here on the left, and each row in this concordance factor table have different combination of 4 species. And each column of that, this number that you see inside this rectangle, is basically the frequency that we see different species together. So for instance, these are also called quartets. So in this case, we have A and B together 8% of the time. You have A and C together, and A and D together 10, other 10 and 10% of the time, right? From those observed proportion, we can obtain the expected probability of this row, and you have that for one row, and you just basically multiply them all to have all the rows. And from that, you obtain a score of the network, and you can see it here. And you notice that it's a summation because if you take the logarithm of that multiplication, you can get a summation. And with this score, basically what you do is you propose a network and see if that score increases or not, right? If it increases, you take that proposed network. If not, you stay on the current network and you go over that fashion to basically search the network space. The problem with this approach is that it can grow very quickly, the concordance factor table, right? You can grow the number of possible combination of 4 grows very fast. And also the network space grows exponentially with a number of reticulations. And this is a problem of big data set, right? And it's not unique in biology. You can find it everywhere in other fields too. You can either have lots of observations that you can see on the left, or you can have lots of variables on the right. So the question is, what can we do with this problem, right? One thing that we can do is to use our old friend, the regression analysis, and all of you are very familiarized with that. And where we have one trait, one observation, but you can also have multiple traits or multiple dimensions. And instead of having one single slope here, we can have like a weighted sum. And each weight is given basically for the coefficient or the coefficient vector that you can see here on the right. And this is just another way to represent the weighted sum. You have multiple, observations. You just stack them all together, and then you have like a vector on the left. Here it is the observed, and you have a matrix here where every column represents a trait, right? And the weight for each trait is given by the coefficient vector. And with that setup, what we want to do is just basically to minimize the observed, which is here on the y, versus the predicted value, which is x and beta. And here I'm presenting you 2 ways to do that. You have the rich and the lasso regression. And you can see here again, you have the prediction and you have the observed. And these 2 ways are important because they constrain the behavior of the coefficients. In the left, for instance, you can see that the coefficients are constrained to be on the sphere, and on the right, you see the coefficients constrained to be in the cube. And if we focus here on the lasso part, we see here the beta hat is the optimal beta, and these red lines represent different error lines, getting closer and closer to the optimal beta. And you can see that one of the corners is clearly closer to the optimal beta. And this is an interesting property because if you look at that corner, you can see that one of the coefficients are being set to be 0, and another coefficient is set to be 1. Specifically, the one that is being set to be 0 are the coefficient number 1. And it makes sense because if you see one of the corners, that corner on beta 1 is definitely more far away from the optimal beta, right? And basically saying, oh, beta 1 is not that important if you compare it with beta 2. And this is what we call a sparse solution. And one way to apply that in biology is to a problem of genome size alignment. So imagine you have alignment. Here we have side 1 to P, and you have millions of sites, and you want to reconstruct a phylogenetic tree. By the way, each row here represents a species. So what you can do is basically ask how much information you have in each site by randomly simulate trees, and ask what is the livelihood of that tree on site one, and on site two, site three, over all the sites. And if you sum all these livelihoods, log livelihoods, you can get the overall livelihood of that random tree. And if you go over that fashion, you can get different livelihood for different random trees. Now, if you flip this table, you can effectively have a regression problem, where the Y here are the livelihoods of different trees, and the traits here are basically the sites, right? How much information you have in every site. And the weight for each site is given by this coefficient vector. Now, if we apply last on this, we know some of these coefficients are going to be zero, right? Why don't we go ahead and set up the first one to be zero? This one is zero, so it means that this first column is zero, or it's not that important. But that column represents one column in the alignment side. So it means that that column in that side, or that side, sorry, is not that important in the alignment. So you can go and reduce on that fashion until you get a very small alignment. The problem of applying this on the concordance factor table is that while we assume that the sites are independent, or in other ways to put this, is the coefficients are kind of independent, you can assume that on the concordance factor table because you can see a lot of correlation among different rows, right? In this case, if we see again the concordance factor table, we see that three species the information of three species are overlapped between two rows, right? So we need to apply a sparse model that account for the correlation among the coefficients. One coefficient, another one has correlation. So we can use something called elastic net, and which is basically something in between. You still constrain the behavior of the coefficient, but it's in between the sphere and the curve. You can see here this weird shape where you still have corners, but in between you have this sphere. And we can apply that as the same pipeline that I presented before. Now, instead of having like an alignment, we have concordance factor table. Instead of having random trees, we have random networks. And instead of applying lasso, we apply elastic net. And again, let's do the same exercise of setting one of these coefficient to be zero, because we know they are going to be zero because they are a sparse model, and you have 1 0 there. And that means that this trait on this column is not that important. But that column represents a row in the original problem, on the row in the concordance factor table. And you go over that fashion until you reduce and compress more and more the concordance factor table. And that's how you can reduce the number of rows. You can also apply the same idea on ensemble learning. Now, up to this point, I've been talking about linear models and straight lines, but you can also apply kind of the same idea on nonlinear models, where you have different nonlinear models, different sublinear models, submodels. And from that, you have a combination of them and get the predicted livelihood. And in this step of combining, you can apply elasticity, and you have like a subselection of submodels. And this is going to be useful later on when we apply on the results part. We're going to go right away to jump to the results part. And we're going to apply with a very, very small data set with 15 rows, which represent this network that we have here. You see here that the hybridization is coming from the species 5 to the clade between 4 and 3, and the number of rows is 15. So if we apply the elastic net here, you can see every color line represents a row in the concordance factor table. And if we increase the lambda parameter, which is a parameter that increases sparsity, or control sparsity, better said, you see a very big values of the lambda. You see none of the rows are selected, all of them are zero. But then when you keep decreasing the lambda parameter, you see that all the rows here are being selected. So probably what we are more interested here is in this region, where some of them are selected, some of them are not. And what I did basically is to take evenly separated subselections from this region, 5 of them. And this is the result that I obtained. So the first one is that if you take 3 and then you compare it with the true network, you can see a distance which is above 0. And you take 5, also above 0. But from 6 rows, you can start seeing that the distance is not 0 anymore. And if you go to 8, you can actually get the true network 97% of the time. Now, what if we take random selection? Instead of just the selection being guided by the model, we take random selected rows. We see that the distance is not 0. And in that case, I'm sorry. And you see here the A rows are, is above 0. So it's not 0, the distance to the true network. What about the running times? And we see here that the red line below, sorry, here, this is the normal, I mean, the amount of time that it takes you if you do the inference with the whole data, which is around 1 minute. But if you take 8 rows, you can see that it takes you around 40 seconds, and the same for the 7 rows. And this is a typical solution that you obtain if you do you kind of infer the network with the subselection. And another important detail that was super interesting to see is that you know that you're selecting rows, but inside those rows you have a different frequency of species, right? So if you see the frequency of the species inside those rows selected, here you can see different patterns. So for instance, in each Y here it represents one species, 1, 2, 3, 4, and 6. And here the lambda parameters again control the sparsity, right? If we have very small lambda, we see all of the rows are selected, so it means all the species, all the frequencies selected. But if you go very big lambda, you actually see none of them, very few are selected. If you see the frequency, you see very early on the elastic net path, some of the species are selected, right? Some you see 3 here and 4, you see in the lighter color. And this is surprising because these three species 3 and species 4 are actually part of the hybridization event. So it was interesting to see that the elastic net model are kind of checking on, okay, these species are important for predicting a livelihood as well. Okay, what about some bigger data set, right? Large scale data set. In this case is 1,365 rows. And this is the network that we want to approach with 2 hybridizations. And you have it here. So if we apply ElasticNet, it's very difficult to tell where is the region where we make the subselection. In this case, you see again, if you have very big lambda parameter, you see none of them are selected, but you keep decreasing, more and more rows are selected. But it's very difficult to tell, oh, this is for sure is the optimal point where you take the subselection, right? For that case, we apply something that I was explaining at the very end of the methods part, which is ensemble learning, which in this case, every row represents a submodel, a learner, and each learner is actually a decision tree. Inside those decision trees, you have different rows that are being used to make the decision tree. And you see here again, if you have a very big lambda, none of the decision trees are used. But if you keep decreasing, more and more decision trees are being selected. But there is a point, an optimal point here, where you can actually tell, oh, this is probably the subselection that I need to look on. So I look at those subselected decision trees, and I look inside those decision trees and see what are the rows that are being part of the subselection. And again, I did the inference based on those subselections, and this is one of the results that I obtained. So this is very close to the optimal point, and this is the beginning basically of the elastic path. And you see here that 21 rows is not enough, 59 is not enough here, but from 289 to 618, 19, sorry, it's getting closer to the optimal network, right? In this case, you have 71% of the time the corrected network. If you take random selection, you really don't get that amount of zero distance to the true network. You can get it 50% of the time here. But then if you go one subselection below here, you get, this in 389, you get actually 17% of the time correct. But then you go back to 40 and then you increase later. So it's very erratic behavior. It's not like here where more rows means more accuracy or less variance on the inference of the network. So yeah, the random, while sometimes random, you can get the right solution, sometimes not. So depending on is somehow a little bit erratic. About the running time, if you see here, the red line here, it represents the amount of time it takes you if you do the network with the whole data set. It's around 4 hours. And if for 619, you can get it around less than 2 hours. And if you are willing, in average, right? And if you are willing to, obtain quick and dirty network, you can also obtain it with 289, and you can obtain it like in half an hour too. But the accuracy here is not that good. It's around 51%, so it's at your own risk. So this is a typical solution that we obtain with subselection. And okay, so one of the main conclusions for all these two examples is that the data set that we're using, the concordance factor itself is correlated, and you have a lot of redundant data. And I want to think or want to reason about this on imagine you're being asked to reconstruct this image that you're seeing right now. And if and you can clearly see that some pixels are more important than the others, right? If they ask you to reconstruct the background or the scene, maybe you don't need all the pixels, you just need one pixel, and then from that you multiply them all. But there are some pixels that are more important probably for the fish itself. You have the eye, which is more important than something on the background, right? So yeah, definitely redundant data. Um, as the data set grows, I conjecture that I think, or I conjecture that ensemble learning might be more optimal because for fitting that model, you really don't need all the rows in the concordance factor. You just need sub-selection of different traits. And when you combine them all, you can get the whole model. So it is something that I mean, can be part of a discussion or something to think about it. From some future work is like, okay, we know that some simulation is working, is having a good behavior, but what about the real data set, right? Well, in the real data set, we don't have a true network. We have something that there is lots of evidence of having hybridization, like a C4 data set. And also, what about the species being selected, the frequency of the species being selected in each subselection? Can we have more control about those? So for that, maybe we can use something called the constraint lasso, which is the same lasso, but we can apply some linear constraint of that by saying, like, for instance, okay, I want the lasso solution, but I want to have this frequency of the species selected above some threshold, something like that. And I believe it is not very well known, or it's not widely used yet on phylogenetics, and that can be an important venue to explore. Thank you very much for your attention. This is a joint work with Ricardo and Claudia, and they guided me over all this project. Thank you very much for all of you. And now, I think as part of the Zoominario, I think I need to share a little bit of my background, where I come from. I come from Peru, very beautiful place. I'm 100% biased on that. You can find in Peru, you can find beautiful places like the Andes. You have Machu Picchu, llamas. You can have very colorful mountains. You have also the Amazon, and you can find the coast as well. With these Nazca lines that are part of the coast, or you can have very ancient civilizations like the Caral with around 5,000 years old. And specifically the place that I came from and come from is from Lima. And Lima, this is a typical Lima time in the plaza. This is one picture of mine, and you can see, the church, the plaza, people gather. And sometimes, if you're lucky, walking around those avenues, you can find people dancing too, very common. Or you can also find people protesting for some justice. And because it's the coast, you can also find the sea. And this is very close to my house, and this is a place called Chorrillos. And I took this picture, and you can find here the boats and very fresh fish as well. And occasionally you can see sea lions as well, among many other species. And actually, in the morning, if you go at 5 a.m., you can find some porpoise, like jumping around. Oh, you also have pelicans and lots of biodiversity. So I want to believe somehow that all this biodiversity, all these colorful places, kind of pushing me to be what I am right now, like a biologist trying to find out some patterns in nature. Okay, thank you very much for your attention, and I think